So today's topic is potential energy diagrams. So looking at a visual representation of reaction rates and what is happening with your potential and kinetic energy throughout. First things first, law of conservation of energy always holds true. So in any chemical reaction, your energy is conserved. What might actually happen is that your potential energy will change, therefore your kinetic energy will change, but the total sum must be the same before and after your reaction. So if potential energy goes up, kinetic energy will go down. If potential energy goes down, your kinetic energy will go up. Now, a couple of terms that you need to keep in mind. The first one's threshold energy. This is the minimum kinetic energy that you need in order to change that kinetic energy into activation energy. So you have to get enough movement in your particles to reach that point so that you can actually have your activated complex. Now, your activated complex is important because what you need to think about, the particles that are created right here are those that will then recombine to make your products. So you break apart your reactants into all their components, their atoms, their ions, whatever it is, and then they will become the activated complex. This transitions into your products when you recombine the new bonds. Now, just briefly, molecules are always in motion, so they're all zooming around. Now, they have to get close enough to another molecule in order to break them apart, because they are attracted to each other, but once they get close enough, they will be repulsed. So they're going to be slowing down as they get closer, and as they slow down, that kinetic energy that's decreasing is going to be changing to potential energy, which is going up. So if they have enough kinetic energy, you will get them close enough to have an effective collision so that you can create your activated complex. Now, two things might happen with your activated complex. One is that you will actually have a collision, enough to sort of break them apart into their different particles, but not enough energy that they stay apart. So there's no reaction because they just recombined and it go right back to the reactants. That is an ineffective collision. The second thing that could happen is to have a complete rearrangement, an effective collision, so that the bonds do form new products. So your reaction occurs, you got past the activated complex, your potential energy as your bonds break is going to change, and you're creating brand new bonds. The difference between these two is your enthalpy. So that goes back to our last unit when we were looking at the heat that's either released or taken in. So this is where the diagrams come in. With an exothermic reaction, you're going to see this. The potential energy of your reactants is higher than the potential energy of your products. So to get to that activated complex, it doesn't really take that much energy. You just have to get to this part to break those bonds, and then it's that downhill sort of spiral to your products. The difference between the potential energy your reactants had and the potential energy your products had is your enthalpy. That's what's given off to your surroundings. So that is exothermic. So in other words, your reactants have more potential energy, which means your products have more kinetic energy, therefore a higher temperature. So when you're colliding all these particles together, you tend to give energy and then they increase their speed and therefore heat up their surroundings. Endothermic's the opposite. You're going to see a decrease in that kinetic energy because what happens, your reactants have a low potential energy, your products have a higher one, so that difference is your enthalpy. You're going to see a decrease in temperature. Also, you're going to see a lot of energy needed to get to your activated complex. So your activation energy is much higher than your overall enthalpy. So to sum up, what you're going to see here, your products have greater potential energy than your reactants. So you're starting down here, you're going to see less energy for subsequent collisions to happen, so it's going to cool down. So your activation energy is much higher than your enthalpy. Your job now is to practice drawing them. Here's 3 examples for you to try. I want you to draw some neat ones, fully label them, try to get your scale more or less when you look at the values of your enthalpy and your activation energy. This is posted on both Google Classrooms as well as D2L, and I believe the answer set is also on D2L for you to take a look at to check your answers. So, good luck!